Okay, so today we will be discussing about the manipulation of light. In this, we'll talk about the polarization of light, Mallus Law, and Birefringence. All these things we'll discuss. Okay, so we'll be talking about the manipulation of light. Okay. So in the past, we have learned about the properties of light, the optical properties, the electromagnetic properties, how light can be used in an optic fiber, and how light amplification can be done. All these things we have learned. We have learned about light sources, how these light has been detected, and now today we'll see how we can manipulate the properties of light. So when we talk about manipulating the properties of light, the first thing we think of is the intensity. So how intensity can be manipulated. Okay, so with this we start today's session, and I give the very first question to you. The electrical susceptibility or permittivity for any given medium is a function of wavelength or frequency of incident light on it. Is this statement true or false? Okay, you say true. And why is it true? You must be having some justification regarding that. You say it's true. Yes, definitely it's true. Why is it true? Why do you think it should be a function of frequency? We know that dielectric constant is a function of frequency, but how do you prove that? Physically or using some mathematical form?
Because permittivity is inversely proportional to omega.
Yes, permittivity is inversely proportional to omega. So, so when we talk about this, so how do we get to this conclusion that permittivity is inversely proportional to omega? Yeah, susceptibility is a function of frequency. So here I'll be doing a very short discussion on how do we get to the conclusion that this dielectric constant is a function of frequency. Okay, so we have electromagnetic waves, and when an electromagnetic waves it passes through a medium, what it does, so suppose this is my electronic orbital, electrons are here, nucleus is here. Okay, this is nucleus, this is the electron. So when an electromagnetic wave passes through it, what it does, it will displace this electron on its orbit. Okay, the electron gets displaced. So what is happening, these electrons will be the electron gets displaced in their orbitals, and it will result in the creation of dipoles. That is, dipoles will be created. Okay, that is okay. Let me admit a few people wants to join. I'm admitting them. So dipoles are created. Okay, so when dipoles are being created, okay, so when dipoles have been created, so what happens, they will undergo some oscillations, and they undergo oscillations under the action of the electric field of this passing EM wave. Okay, so this happens, and when this undergoes oscillations, so what happens over here, the force acting on these dipoles, what will be the force that will be acting on these dipoles? First of all, there will be an electric restoring force. Okay, there will be an electric restoring force, elastic restoring force, that would be proportional to the displacement. This elastic restoring force will be proportional to displacement. Say R over here is displacement. Okay, and this is the displacement from its equilibrium position. So if an electron is over here, it gets displaced from its equilibrium position. It comes over here, so this is the displacement of the electron. So electron gets displaced from its equilibrium position. So a restoring force will be active and will try to bring the electron back to its mean position, equilibrium position. So this restoring force will act on it. What are the other forces that will act? The other forces that is going to act will be that these electrons will be oscillating. Okay, there will be oscillation of the electrons. Okay, like like a pendulum. These electrons will be oscillating, and there will be a damping force associated with it, and this damping force will be proportional to the velocity. So another force that will be acting on this would be a damping force. Okay, F damping. Sorry, I shouldn't be writing force. This F damping, this F damping will be proportional to the velocity of the electron. And then what will happen? Electrons start oscillating. There will be a damping force that is proportional to velocity. Then we assume that the nucleus is at rest, and then there is another force that will be acting on the electron. That will be the electric force of the electromagnetic wave. That is, the electron will be so actually this electric force is what that is acting on the electron. Because of the electric field, the electron gets displaced. So this driving force, or the electric force, will be equivalent to E of E vector, which is the electric field of the light vector, the electric field component of the light vector. And this E vector can be written as some magnitude of E times e to the power I omega t. Like let's take it a complex number. So if we write the equation of motion of this, what will we get? We get, what is the equation of motion? We will get m d2 r. M here, let's say, is the mass. Okay, m is the mass. d2r dt square is equal to whatever f restoring will be minus m omega 0 square. Here omega square or omega 0 square is the natural frequency, resonance frequency of the electron with which it is trying to oscillate about its equilibrium position. Okay, omega 0 r. Okay, minus, there will be some damping, so there will be a damping coefficient associated with this. This damping coefficient, say, is gamma. Okay, this will be dr dt, and of course an electric force is associated with it, that is E of E vector. Okay, now if you solve this differential equation, so this is a second order differential equation. Now you need to solve this differential equation. In your mathematics class, you must have learned how to solve second order differential equation. That is, decompose it into a complementary answer and a particular integral answer. We'll focus on the complementary answer. And when we try to solve this, what answer we'll get? We will get, so this is a second order differential equation, and when we solve this, we will get E of E vector, okay, by m times 1 by, okay, this is omega 0, which is the natural frequency of the oscillating this, minus I, let's say gamma omega. Okay, this gamma will be gamma by n. Let's say I'm representing it by g. Okay, so this g over here is actually gamma by m is equal to d. Okay, and yeah. And the E vector, as I said, will be equivalent to E0 e to the power I omega t. Okay, E0 vector. Okay, so this is how you have your this thing. Now, as I said, this dipoles are being created. Then the dipole moment associated with it will be displacement is there, and say the electronic charge. Let's multiply it with the electronic charge of an electron. So dipole moment of one electron will be this E of r vector. So this will be E square the whole of this, if you try to plug in r in this. Okay, this becomes E square. Now there will be n number of such dipoles. Okay, n dipoles will be created. Now if n number of dipoles will be created, and let's say n dipoles are there per unit volume, so the polarization here, I mean the net dipole moment per unit volume will be given by n of small p. Okay, and that is equivalent to, as I say, that we know from dielectric courses, electromagnetic courses, that this is equivalent to epsilon 0 chi e, where chi is the susceptibility. Okay, so this chi will now can be written as P by, okay, P by epsilon 0 E. Okay, right? Am I right or wrong? Okay, NP by epsilon 0 E, and P over here is equal to NP. So we can substitute P over here. Okay, P is NP, okay, epsilon 0 E, and P is E of R. So we substitute ER over here. That will be equivalent to NE, displacement vector epsilon 0 E. Now just plug in R over here. If we plug in R over here, so my susceptibility will be N E square by epsilon 0 M. Okay, E gets cancelled and we will be left with right, omega 0 square minus omega 0, omega square minus I G omega. I hope I'm right. Am I? Yes, this is right. Yes. So we see that susceptibility is a function of, what do we see? We see that the susceptibility is a function of frequency. Okay. So now we say that, yeah, the susceptibility is a function of frequency. And if we want to know about permittivity, how we go about permittivity, so we know that the displacement vector is equivalent to P plus epsilon 0 E. Okay, and this epsilon 0 E we can convert into susceptibility. This will be equivalent to some epsilon times E, where my epsilon, we also convert P. Okay, P is epsilon 0 chi E. Okay, P is epsilon 0 chi E. So epsilon will be equivalent to, so my epsilon is equivalent to what? Epsilon will be equivalent to epsilon 0 1 plus chi. Okay, so if chi is a function of frequency, so epsilon will also be a function of frequency. Okay, and if they are function of frequency, there will be function of wavelength as well. Okay, so I hope you got the answer. Okay, so the answer is true, and this is how, by this mathematical and physical argument, we come to the conclusion that the permittivity is a function of frequency. Okay, moving on. Next question. Can you please answer this question? Please answer this question. Polarization describes the evolution of dash of the electric field vector.
B.
B, yeah, transverse component. Why do you say transverse component? Why not longitudinal component?
Because they are perpendicular to each other.
What is perpendicular to each other?
The X and Y component of electric field.
The X and Y component of electric field is... Yeah. So, why is my recording not working? Yeah. Okay. So polarization is basically so light is actually symmetric. The light vector, it rotates in all directions symmetrically. Okay, it oscillates or vibrates in all directions symmetrically. Polarization means this light vector is vibrating in one particular direction. That is the meaning of polarization of light. That is decomposing the motion of the decomposing the tip of the electric vector. It's vibrating in only one particular direction. either perpendicularly or horizontally or in a circular direction or in an elliptical direction. Okay, that's what you call polarization. So in an electromagnetic wave, the electric fields, as Deep Patel has already said, that the electric field and magnetic field are perpendicular to each other, and also electric field and magnetic field are perpendicular to the direction of propagation. That is the meaning of transverse wave. E and M are perpendicular to the direction of propagation, while in longitudinal component, what happens, it is not it is in the direction of propagation. Okay, so that way you cannot just you cannot just confine the motion of the vibrations of the electric field in one particular direction. Okay, because it is in the direction of propagation, propagating in the same direction as the direction of the wave. If we are confining the motion of the wave. But in the in this thing, in our transverse wave, the E vector is perpendicular to the direction of propagation, and so we can see polarization in that. And so the polarization describes the evolution of the transverse nature. Okay, so now let's move on to the next question. Okay, let us move on to the next question. Okay, this is a reason and assertion type question. In an optical fiber, any optical power is absorbed and can be converted to heat energy. Second, the reason they are giving is that molecular resonance happens at a higher frequency compared to the electronic resonance. So, what do you say? What is the correct answer to this? Not aware. Okay. Okay, I'll tell you. So, in an optical fiber, we know that there is attenuation in certain wavelength range. Okay, in certain wavelength range, there might be scattering. But we are talking about absorption. In certain wavelength range, like beyond 1.6 micrometers, there is infrared absorption. Okay, so there is absorption, and this absorption in certain wavelength will definitely carry certain wavelengths get absorbed. So that wavelength associated with it has some energy with it. Okay, and that energy can be converted to heat energy. So absorbed power can be converted to heat energy. Okay, but is it because molecular resonance happens at a higher frequency compared to electronic resonance? So first, we need to understand, is this statement or the reason is correct or not? So, so if we look at the graph, if you look into the graph, we had already done the derivation of the permittivity with the frequency. So what do we see? We see the graph goes something like this. Okay. So if I now choose a different color, let's me choose a different color. So this part, this is omega, this is infrared, and this is UV, ultraviolet. Okay, so this is the electronic resonance, that is only electrons are involved. And the what is this resonance? Okay, what is this? This is because of molecular resonance, that is atomic dipoles. Molecules, that is one atom is associated with another atom, and atomic dipoles or molecular dipoles are created. So there will be some molecular resonance also, but these are all frequency specific. Okay, it happens at a lower frequency. Okay, so the statement over here, molecular resonance happens as a higher frequency compared to electronic resonance, is wrong. So R is false. Okay, so the only option which says R is false is C. So A is true, R is false. Okay, I hope you got it. So now next question. Detect the type of light at the source, like at this point. This is the source. Okay, you need to detect the type of light. Now, how do you detect that? You will detect that on the basis of what observation you get. Okay, so this light, some light, it can be anything. It can be a polarized light, unpolarized light, circularly polarized, elliptically polarized, any light. Or it can be mixture of two types of light. Okay, so any light is going through some analyzer. This analyzer has a capability to polarize it. Okay, to polarize the light. Now this analyzer is rotated across 360 degree and you don't see any variation in intensity. So what do you say? What type of light is there? What type of light are we passing? What is number one? What type of light is being passed?
Polarized,
Yeah, polarized light. What type of polarization? Circular.
circularly.
Okay. You are partially correct, I would say. Not completely, partially. It is a circularly polarized light. But what will happen if I pass unpolarized light?
Intensity would decrease.
Why do you say intensity will decrease? I'm saying that there is no variation in intensity. Here I'm not talking about intensity. I'm not talking about intensity.
What
And
was the question?
I'm saying that after rotating the analyzer, there is no variation in intensity. I am not talking about what is the intensity over here. I'm just asking what type of light source is here. What kind of polarization of the light is there? I am not measuring any intensity over here. I'm just seeing what intensity is over here. So I'm just rotating it. I'm seeing there is no variation in intensity. So what other type of light can be here? It can be an unpolarized light, right? If I have an unpolarized light, I pass it through an analyzer. And now this unpolarized light will get polarized whatever be the direction in the direction of the direction of the axis of the analyzer. So this is my light, okay, and suppose this is my analyzer, okay. It's say in this direction. So here the electric field is symmetrically vibrating in all directions. This is unpolarized light. It goes here, I'll get this, okay. Now suppose I rotate my this analyzer, okay. Here whatever I got something. Now I rotate my analyzer, I'm sorry. Suppose I rotate my analyzer in some direction, okay. Say in this direction. So here, this is unpolarized light. It goes over here. What will I get over here? Okay, what will I get? I'll get something like this. Always whatever intensity, say the intensity over here is I0. Always the intensity over here will be I0 by 2, right? If an unpolarized light is there.
Yes.
Understood? Understood. So I'm saying there is no variation in intensity. It will always remain I by 2, no matter how much angle did I rotate it. Okay, no, there is no variation in intensity, so it can be an unpolarized light. And circularly polarized, as you say, it's completely circular. It itself is going through. Think of it. What would be the answer? Think about the next one. Okay, so we are getting two maxima and two zeros. What will be the answer? What kind of light should be there? Hello. Yeah. Yeah, tell me. So this will be a linearly polarized light. I think someone answered. I was not able to listen to it because of my internet issues. Okay, so this will be a linearly polarized light. Why? Because a light which is linearly polarized, it will be in one direction. Okay, so here I'll show you. Yeah, so suppose it is in this direction. So it is in this direction. You have an analyzer. Suppose it is like this. So we'll get one maxima. Okay. Sorry, one minima. Zero. Completely zero. It has been shown. And suppose it is like this, and the analyzer is also like this. Then we'll get a maxima. Okay. So this way, if we rotate two times, so two times we'll get a maxima, and two times we'll get a zero. Okay. Now what about the last one? Okay, analyzer, we are getting two maxima but two minima. We are not getting a zero, we are getting a minimum. What could be the answer?
Elliptically polarized.
Correct. Elliptically polarized. This will be an elliptically polarized light, but along with that, elliptically polarized or plus some unpolarized light can also be there. Okay, or some linearly polarized plus an unpolarized light. Okay, because you can use the logic of unpolarized light from the first question. Okay, I have already told you what will happen if an unpolarized light pass through an analyzer. Okay, so this is just a pictorial representation which has been taken from the book, The Meaning of Linearly Polarized, Circularly Polarized. And circularly polarized is in two directions. One is the right, the other one is left. Right means when it is rotating clockwise, and the left is when it is rotating anti-clockwise. Okay. Okay, so this is just a pictorial representation of how a polarized light looks. The next question is on Faraday isolator. What is a Faraday isolator? Where is the Faraday isolator? Okay, I'll tell you over here. Okay, so at times what happens is like we have some source. Okay, we'll have some source. Now there it goes to some components. Say some components are here. Okay, we have some components. Now the source gets reflected, and then it again comes back. Okay, so there is some back reflection. Okay, so in the back reflection, what will happen? It's like it will be causing some instability in your cavity, whatever cavity is. Say we have a laser source, so it goes out and it again gets a back reflection over here. It comes back inside the cavity. This will be quite unstable to the cavity. So what we do, we use some optical isolators. Okay, what do? We use some optical isolator. What is an optical isolator? An optical isolator, it just allows or transmits allows transmission of light, transmits light only in one direction. Okay, it just transmits light in one direction. Only in one direction. Okay, there is no reverse back reflection of light allowed for an optical isolator. So we call them a non-reciprocal devices or non-reciprocal isolator. Okay, why we need such an optical isolator? This will, why do we need? This will prevent some unwanted feedback. Okay, unwanted feedback. Okay, this will prevent any unwanted feedback into our optical oscillator. Okay, oscillator. Example of an optical isolator. Example of an optical oscillator.
Laser.
Yes, that is a laser. Okay, So laser cavity, we have two mirrors, laser goes out, it will hit some component and then comes back, couple with the laser again, but this can be a detrimental to my laser because the extra power, extra energy will be given to it. Yeah. So we do not want this. We want only one way. Laser should go out. Like we need to collect it. Okay, we need to collect the laser. Okay, so for this we use some isolators, and those isolators are called Faraday isolator because it follows the Faraday law. Okay, so Faraday isolator is not required for dash in most applications. So it is not required for low power sources. Okay, it is never required for a low power source. Okay, because in high power source we do need Faraday oscillator because we don't want any reflection, any back reflection, even 0.1% back reflection that can damage my high power source. Okay, so next is let's move on to the next question. The next is, which one of the following is a non-reciprocal device? I've already told you which is a non-reciprocal device. What is a non-reciprocal device?
C.
Yeah, that's a Faraday rotator. It works on Faraday effect. What is Faraday effect? What is Faraday effect? Faraday effect means it causes rotation of the polarization. And this rotation of the polarization is proportional to the magnetic field which is along the direction of light. That is Faraday effect. Okay, that is the polarization gets rotated by some angle. Okay, theta. And that is proportional to the magnetic field and okay. So let us move on to the next question. I hope you know about birefringence. What is birefringence? What is birefringence? It's sort of a double refraction. Chalo, I gave you one hint. What is birefringence? I told you double refraction. Double refraction. Okay, what is double refraction?
Associated with anisotropic medium.
Yes. So in certain anisotropic medium, what happens that the refractive index is not the same in all directions. Say in x and y direction, the refractive index are different. So when any light passes through it, then you'll get two types of rays out of it. One will be the ordinary ray, and this ordinary ray will follow the Snell's law. Okay, the other will be an extraordinary ray. The extraordinary ray does not follow any of these Snell's law or something. So it looks something like this. Suppose this is some crystal. Mostly we call them W refraction crystal, such as calcite, quartz. These are all W refracting crystals. That is, they are anisotropic in nature. Okay, so here we have a light ray. So what happens when it goes? There will be the polarization in two directions. Okay, so it goes something like this. Okay, and it comes out. Say I'll call this as the extraordinary ray, and then there will be another thing, and this happens because of anisotropy in the medium. Okay, and this will be the ordinary ray. This would be the direction of polarization of the ordinary ray, and this might be the direction, that is, they have two different directions of polarization. Okay, they are different by some phase in between them. Okay. So now we have an extraordinary ray and ordinary refractive indices of material for a half-wave plate. So half-wave plate is basically a retardation plate. It is and another retardation plate is a quarter-wave plate. So these retardation plates are used to introduce some phase difference between the ordinary and the extraordinary rays. Okay, so you want to know what will be the thickness of the plate in micrometers for working wavelength of 1550, that is infrared region. Do you know how to solve this problem? Can you please tell me how to solve this problem? How does retardation plates work? So it introduces some path difference. So what will you do? It
Using the
int-
formula of
yeah.
phase retardation.
Yeah, we will use the formula of phase retardation. Okay. So basically, these plates have some thickness. So some path difference will be introduced in the ordinary and the extraordinary ray. We have Ne and N0 as the refractive indices for this ordinary. So this is No, a refractive index of the ordinary ray. This is Ne, the refractive index of the extraordinary ray. Then the path difference will be depending on the refractive index. So what kind of path difference will it introduce if it has a thickness of D? The path difference introduced will be N0, say N0 minus N of E times D. This is the path difference. Okay. Now, if the path difference is this, then delta, that is the phase difference, will be 2 pi by lambda. Just 2 pi lambda, multiply it by 2 pi by lambda. You'll get the phase difference. Okay. That will be this. So it is a, what is it? It is a half wave plate. So what is the path difference or phase difference because of the half wave plate?
Pi.
Pi. Pi is the phase difference. So you can just say pi is equal to 2 pi by lambda n0 minus ne. Okay. So now what? Lambda is equal to, just a second, I'm making some mistake. So d is equal to lambda by 2 n0 minus ne. Yeah, here it will be Ne. Okay. So this will be the thickness. So what are we supposed to find? What will be the thickness of the plate in micrometer? So we'll use this formula. Okay.
It's Ne minus NO, I think.
Yeah, any. So I'm not placing a complete minus sign. I'm saying whichever will be bigger. So if you say any minus No, okay. Let's say any minus No. Okay. So we will have this Ne minus No times t is equal to pi. So whatever I did, just confirm these values. You know what is lambda, you know what is Ne, you know what is No. So that will be equivalent to this. This much would be the thickness of the plate okay, of the plate, which will introduce a path difference of how much? Half wave plate introduces a path difference of how much? Lambda by 2. That's why it's called a half wave plate. Next question.
Excuse ma'am.
Yes.
Ma'am, in the last question, if we have we will have to write the answer in scientific notation, then how we will write
Okay,
2.52 micrometer in scientific notation.
2.52 in scientific notation. So
Yes, ma'am.
this is micrometers. Okay. So basically this will be 2.52 times 1e minus 6 meters. Or you can also just, take this point to the other side and manipulate, and you will get something over here. Like minus 6 will become minus 8, 9, 6, 7, 8. No, minus 8. 252 times 1e minus 8 meters. Got the point?
Yes, ma'am. Yes, ma'am. Thank you.
Or it can also be written as 25.2 1e minus this will minus 6 minus 7 meters. Okay?
Okay, ma'am. Thank you.
Yeah? Next, the refractive index is higher at dash region due to an electronic resonance. I have just now showed you in the previous two questions how the graph looks like. So what will be the answer to this? We have already drawn the graph. We need the electronic resonance. So tell me, where do we get the electronic resonance? The graph is something. How was the graph? Tell me. Yeah. So the graph is something like this. This is what, and this is what resonance. This is around, here it's around
A.
UV. This is IR. What is the answer?
Yeah.
Sorry.
First was IR and
Sorry. And this is frequency now, right? You're right, Deep. Uh, this is IR and this is UV. Refractive index is higher at dash spectral region due to electronic resonance. This side is electronic resonance. So refractive index will be higher at the UV side. Why IR? Why did you say IR? I think the answer will be UV side. Just check in the book and let me know, okay? And why did you say IR? Can I know that?
because I thought refractive index is inversely proportional to frequency.
No. How do you say, how do you write refractive index in terms of, say, see, so we know this, this was the graph for EFSA. So refractive index graph will be same, no? This is EFSA, right? We have drawn the graph for EFSA. This is EFSA. So refractive index is equal to root over EFSA by EFSA R, or say EFSA R only. EFSA not. So it will be following the same trend. Okay, just check and let me know. Okay, any confusion that you have, please let me know. Okay.
Yes.
Okay, what will be the polarization state of transmitted light from a half-wave plate if the incident beam is circularly polarized? It's a half-wave plate. What will be the phase difference?
Pi.
Yes. Pi.
D.
Yes. It will be right circularly polarized. So what is actually happening? Um, so just reverse it. This is left circularly polarized. Now increase the phase difference. The phase difference introduced will be pi. This will get reversed, simply reversed. Okay. So it will become right circularly polarized. Okay. This is one way of doing it. Another way of doing it is it's like you can write the difference between the two electric vectors, that is the x component and the y component. Suppose ex is equal to e0 cos of omega t minus kz, and ey is equal to e0 sine of omega t minus kz. Okay, so what is going to happen if I introduce a phase difference of pi in one of the components? Say x gets a phase difference e0 cos of omega t minus kz. Now this pi will be sine tan cos. Okay, minus pi. Sorry, plus pi. A phase difference of plus pi is introduced, and ey remains e0 sine of omega t minus kz. Okay, and this is ey. So this component now becomes, am I making some mistake? No, this will now again reverse its sign. It will simply reverse its sign. Okay, cos of omega t minus kz. So whatever polarization you had previously, it will be the reverse of that polarization. So left circularly polarized becomes right circularly polarized. If I have a right circularly polarized, it will become left circularly polarized when it is passed through a half-wave plate. Okay. Now next question. Suppose you are given a source. Now that source is circularly polarized. What will be the orientation of the transmission axis of the analyzer to get the maximum output power at the detector? We have done this twice. You know the answer? B, 90 degree. Sure? We did one question, no? What is the source? We have an analyzer over here. Okay. And the analyzer is rotated through 360 degree. And we didn't have no variation in intensity.
D.
Right. Circularly polarized light doesn't matter. Now this explanation for this is that in circular polarized we have EX and EY. Okay, both this EX and EY are orthogonal to each other and they are equal in magnitude, but they are 90 degree out of phase of each other. One is sine, the other one is cos. Okay, we have seen mathematically as well. So if I put one of my component as 0, say EX becomes 0, then the other will be maximum and this will happen vice versa. So the analyzer output will always give the same, there will be no variation of the frequency no matter what is the angle between the analyzer and my polarized light, no matter, it is irrespective of the analyzer angle. Okay, so any of the above is the correct answer. Now next question. This is a very interesting question. You'll get these type of questions in the exam, and I think these type of questions also are there in your assignments as well. We have a circularly polarized light. I'm passing it through a quarter wave plate. So what will it become? Here, what type of light will it become? Will it become right circularly polarized? Huh?
Linearly polarized.
Correct. So when you pass a circularly polarized light through a quarter wave plate introduces a phase difference of how much?
Pi by 2.
Pi by 2 का phase difference, 90 degree phase difference. Already they are 90 degree out of phase. Now I introduce another 90 degree phase difference. So if you write the x component is a sine omega t and y component, here I'm not considering left or right. The main thing is both of them are 90 degree out of phase. Okay, y component is a, say not a, b of cos omega t. I'm not taking whether they are having a same amplitude or not. Okay, so a phase difference of say 90 degree introduce, introduce a phase difference of 90 degree. A sine omega t, y may introduce, let's introduce in y cos of say omega t, say minus 90 degree. Okay, plus also in 10 cos. Okay, it's plus 90 degree. So this will become minus b sine of omega t. Am I right? Am I right? Yeah. So y is equal to minus b. Let's say sine omega t is x by a. Okay. So this is a linearly polarized light. The equation of a straight line, right? This is the equation of a straight line. So this becomes linearly polarized. So now if I pass my linearly polarized light through an analyzer and rotate it through by 360 degree, what will be your observation for the intensity?
2 maxima and 2
Two
zeros.
zeros, correct. 2 maxima and 2 zeros. These are very, intuitive questions. So you should try practicing these questions a lot because these clear your concepts of how the polarizations, like what type of polarization is it and how it can be changed, how you can manipulate the intensity of light. This is the whole intuition of manipulating the intensity of light. This is how by introducing analyzers, polarizers, or some retardation plates, we can manipulate the intensity of the light. Okay, so now let's move on to the next question. Next question is also on the intensity of light, but a famous law directs this. Can you please tell me what would be the law that would, what is the law? You must have studied about that law, which talks about the intensity related to the angle between the light and the analyzer or polarizer. You understood my question?
Mallus Law.
Yeah, Mallus law. Mallus law relates the intensity of the light with that of the angle through which my analyzer or polarizer is kept with respect to my light source. So I have an unpolarized light. Okay. See, this unpolarized light has an intensity of I0. Okay. This 10 is I0. Okay. Now it is passing through two polarizers. So this is my unpolarized light. Okay. It is passing through P1 and then it is passing through P2. Okay. After passing through P1, it will get some intensity, say I1. After passing through P2, it will get some intensity, say I2. Okay. Now the angle between P1 and P2 is 30 degrees. I know my theta 1 2 लिखते हैं. Okay, let's write theta 1 2. Theta 1 2 is equal to 30 degrees to each other. We need to calculate the intensity of the transmitted wave. That is, we need to calculate I2. And how are you going to do that? I'll tell you. Can you guys tell me?
7.5 is the answer.
7.5, sure?
Yes.
100%?
Yes.
7.5.
3.7 something.
3.7. Sajdeen is right. And I'll tell you, Deep, what would be your mistake. Your mistake is when you are taking cos square 30. Cos square 30 is, should be root over 3 by 2 whole square. That will be 3 by 4. Okay. You must have taken 3 by 2.
Yes.
Right. So please be careful of this because when I was calculating it, I also made the same mistake. And I was also a bit confused. Why am I getting this mistake? Okay. So be careful while doing these calculations. So how am I getting this? It's very simple. I0 after passing through P1 will become I0 by 2. Now I am passing it to P2. Mallus Law. There is Mallus Law. Mallus Law says that this will be I0 by 2 cos square of the angle through which it is going. That angle is 30 degrees. Okay? Simple. Very simple question but very intuitive. So intensity of light I1 after passing it becomes I0 by 2. Unpolarized gets polarized after passing through P1. Only half the intensity will be transmitted. Okay? By Mallus Law, the transmitted light transmitted through P2 will be given by I2 is equal to I1 cos square. So I2 is equal to I1 cos square. I1 is I0 by 2 cos square 30 degree. That is I10 by 2 cos square 30 degrees 3 by 2. No, 3 by 4. See, again I did the same mistake. That will be 15 by 4. That will be 3.75. Let me see the unit. Microwatt per centimeter square. Clear? Simple topic. Very easy. Right?
Yes.
Yes, ma'am.
Right. So mostly you'll get these type of questions. The intensity variation. You might also get questions related to Faraday rotation. Like what is the Faraday angle, Faraday constant? If this much magnetic field is implied and this is the extent of rotation, what is Faraday constant? And Faraday constant is dependent on the wavelength. Okay. And what type of light is passing through, or the intensity variation is this, how much should be your what should be the light at the source, or how can you convert a circularly polarized light to to a polarized linearly polarized light, or you are given an elliptically polarized light, how can you convert that to a circular polarized light? Okay, so you might need a combination of retardation plates with an analyzer. It should be at some angle. So that's how the whole idea of this topic is manipulating the intensity of the light. Okay, all clear?
Yes, ma'am.
Okay, thank you so much, class.